We are to use the shell method to find the volume generated by rotating the region bounded by x equals 7y squared, y greater than or equal to 0, and x equals 7 about the line y equals 2. So that region is drawn here, and that region that we are going to rotate then would be this region here that's bounded by those restraints. So what we'll do then is figure out, well, where would that same section exist if we rotate it about the line y equals 2. And so what we would have is this green part here would rotate about the line y equals 2 and would be here. And then this black part here would rotate about that line, and it would be here. And then the x-axis, then, that part of the constraint, this part here, would rotate around and be here. Okay, and we're supposed to use the shell method. Now what that means then is that we will draw a section that will be parallel to the axis of rotation. And so we would have a rectangle that looks something like this. And then if I rotate it around that line y equals 2, we would wind up with a shell that would look something like this. And the thickness of that shell is going up and down, so that's going to be a delta y. So we know that our variable of integration, when we do this, and therefore the variable that we're going to have to describe all these functions in, will be y. Okay, so something that we need to do then is cut this shell open and then redraw it. And if we did, we'd have something that looks like this. It would be a rectangular solid, and that thickness would be that delta y. And then this dimension would just be the circumference of that shell. So how would we describe the circumference of that shell? Well, first of all, we'd have to know the radius. Then, so that would be this radius here, which would correspond to this radius here. Now, where this hits this function here would be at a dot that we might call x sub I, y sub I. And the radius then of that shell would just then be the distance from the line y equals 2 to whatever this y sub I coordinate is. And that distance then would just be 2 minus y sub I. So then the circumference of the shell then will correspond to this dimension of this rectangular solid, and that dimension then would be 2 pi times 2 minus y sub I. Then the horizontal dimension here would be then the distance from this edge of the shell to this edge of the shell. I'll do that in blue. This edge of the shell to this edge of the shell. Well, this edge of the shell, this one that's farthest to the right, happens at 7. And it happens at 7 no matter where we draw that shell. And then the left edge of the shell here is going to occur just at x sub I. So we could say then that that dimension of that shell would be 7 minus x sub I, but we want everything expressed in terms of y. And so what we'll do then is convert that to 7 minus 7y sub I squared, and we know that we can do that because we have this relationship between x and y everywhere along that curve. So then we can write that dimension of that rectangular solid as 7 minus 7y sub I squared. Now we can describe an individual volume of that, or the volume of one of those shells as 2 pi times 2 minus y sub I times 7 minus 7y sub I squared times delta y. And if I'm going to work with this, I think it's going to be easier if I will factor a 7 out of this factor here. I think I'll factor out a 7 out of that factor. So what we would wind up with then is v sub I equals 14 pi times 2 minus y sub I times 1 minus y sub I squared delta y. Then, if I was to get an estimate for the volume of that entire solid that would be generated by rotating that region about the line x equals 2, it would be a sum of these shells from I equals 1 to n, 14 pi, 2 minus y sub I, 1 minus y sub I squared, delta y. And an exact measurement of that volume I could get by finding the limit as n goes to infinity of the sum I equals 1 to n, 14 pi, 2 minus y sub I, 1 minus y sub I squared, delta y. And then that we can actually evaluate if we convert it to an integral, which would be 14 pi times an integral. Now, this integral then we need to find some limits of integration for. So from where to where do we perform this measurement of these volumes? Well, we're describing this in terms of y. And this happens from the point where y is 0 to the point where y equals 1. And so our limits of integration will be 0 to 1. And then we have 2 minus y times 1 minus y squared dy. If I'm going to evaluate this, I think what I'll do first is multiply out. So we would have 2 minus 2y squared minus y plus y cubed dy. And then we can integrate. So we'll have 14 pi times 2y minus 2/3 y cubed minus 1/2 y squared plus 1/4 y to the 4th, evaluated from 0 to 1. So we'll have 14 pi times 2 minus 2/3 minus 1/2 plus 1/4 when we substitute 1 for each of those y values. And then we will subtract from that what we would get if we substitute 0 in for each of those y values, which will just be 0. And so now we have 14 pi times, and we would probably need to express all of these values in here in terms of twelfths. 24 twelfths minus 8 twelfths minus 6 twelfths plus 3 twelfths. And then combining all this, we would have 14 pi times 13 twelfths, which then we could reduce the 12 and the 14 to a 7 and a 6. And 7 times 13 is 91, so we would have 91 pi over 6. And that would be the volume of the solid that is generated by rotating the region bounded by these graphs about the line y equals 2.